liquid solids and intermolecular forces. So we're going to be talking about the different states of matter, and we're just describing like the physical state, not matter by composition, just the physical states, and the intermolecular forces that are holding together the particles in each specific substance. So intermolecular forces, I like to abbreviate that as IMFs, and those are the forces of attraction that you have between particles in a substance, but also repulsions, not just attraction. And you will see like some specific examples. The IMFs are going to depend on the charge of the particle, if you have a charge, or if there's like a charge displacement in your particle, and also the distance between the particles. There are two major forces in every substance. One of them we already know, and those are the chemical bonds. You know that we have chemical bonds that are holding together the atoms in a compound, and we have different types. We went over covalent bonds and also ionic bonds. Your chemical bonds are intramolecular forces because they're happening between the same molecule. It's your chemical bonds are holding the atoms in one molecule together. Like for example, if you look at the water molecule, and this is a covalent compound because there's no metal in there, and your electrons are being shared. So you have your water molecule, your atoms, hydrogens, your two hydrogens and your oxygen. They are chemically bonded by that blue line, which is the sharing of two electrons, holding together the hydrogen and the oxygen, and then the hydrogen and the oxygen. So it's intramolecular because this is happening in just the one water molecule. And depending on your chemical bonds, we can determine the shape, if it's a linear molecule, if it's a tetrahedral, right, on all of those different geometries, and also the polarity. So polarity, we went over like polar bonds a little bit, and I'm going over polar bonds again in just a moment. And I have also an example here for ionic compounds, where you have a chemical bond, which is an ionic bond because that bond is happening between opposite charges. So it's an electrostatic attraction between opposite charges. There's transfer of electrons. Your metal is losing, your non-metal is gaining, forming your charges, and then the attraction between those opposite charges will give you your ionic bond. So your covalent and ionic bonds, those are intramolecular forces. Now, intermolecular forces, which is what we're going to spend the rest of the time talking about, are those forces that we have between particles. Okay? So you have particle 1, you have particle 2, and they are attracted by different forces. Okay? Those are your intermolecular forces. Now, depending on the intermolecular force that you have, right, they're going to have different strengths, and depending on the strength of your intermolecular forces, we're going to have different types of physical states. And we can actually go from one physical state to a different one, and that's a physical change, and that can happen if we change temperature or amount of kinetic energy. That it's something that we're going to look also later on. So I did my diagram here. I have 1 water molecule, 2 water molecules, 3 water molecules. It's a simplification. In just 1 drop of water, you will have like millions of water molecules. So this is a simplification. 3 is more than enough to show you what I want you to see. So you have your water molecule, and you have your atoms bonded together by your chemical bonds, your covalent bonds right here. You have a second water molecule and a third water molecule. You have your chemical bonds in all of them, and then my orange lines here, dashed lines, represent the intermolecular forces. So intermolecular forces are happening between different water molecules. Okay? So that water molecule feels an attraction for this one, feels an attraction for that one. This one feels attraction for this one, feels attraction for that one, and there's attraction between all of them. And those attractions between your different water molecules are your intermolecular forces. Now, your chemical bonds are stronger than your intermolecular forces. We can actually break intermolecular forces changing temperature. You can evaporate water. Water goes from a liquid to a gas by increasing the temperature. You're not changing the composition of your water molecule. Your hydrogens and your oxygen atom, they are still chemically bonded when you go from a liquid to a gas. So there's no breaking of chemical bonds. There's breaking of your intermolecular forces, but not chemical bonds, which means that your chemical bonds, they are stronger than your intermolecular forces. Okay? For you to break a chemical bond, that it's a chemical change. Okay? And then you're breaking chemical bonds, a chemical reaction is happening, and you're forming new bonds in your products. Okay? So this is just going over some different properties for the physical state, solid, liquids, and gases, and I'm sure you have seen this before. I even represent the three physical states in the same notation. So for you to go or to move from one physical state to a different one, what is happening is that we're breaking intermolecular forces. When we talk about gases, we went over like all properties for gases, the relationship between the properties of a gas, the volume, the pressure, the temperature, amount of gas, the relationship between those properties, assuming that there's no attraction between the gas particles. Okay? So we're going to do like something similar here. Strong attraction in your particles for a solid. Then we have the liquids with the strength in the attractions between solids and gases. So these ones are weaker than what you have in your solids, but they are stronger than the attractions that you will feel in that your gas particles will feel between themselves. So your liquids, they feel attraction. Your particles, they do feel attraction among them because they are like close to each other. And then in gases, since we have a large distance between the gas particles, then we assume that there's no attraction at all between gas particles, which is not true. There's an attraction, but it's super weak in comparison to this one or this one. Okay? So the attraction of the between the particles in each phase or each physical state here, it's what actually determines the properties that you have for each physical state. Strong attraction, your particles are super close to each other, so we have a fixed volume and a fixed shape. For your solids, because you have super strong attraction between your particles, they're not moving around. For your liquids, we have moderate attractions between the particles in a liquid. They can flow, they can move around, but they are still close enough to feel attraction for each other. So we do have a fixed volume for liquids, not a fixed shape. And then in gases, your particles are super far away from each other. So there's like super weak attraction, or even we say that there's no attraction between them. And that's why for gases, we don't have a defined volume because the particles can move around. There's no attraction between them and there's no defined shape. Okay? So your gases, they will have the volume and the shape of a container. For your liquids, the liquids, they will have the shape of the container, but not the volume. The volume is defined. Okay? And then for your solids, you do have a fixed volume and a fixed shape. So if you increase the temperature, which means that you're increasing kinetic energy here, decreasing potential energy, which is the energy associated with a position, right? High potential energy, low kinetic energy, because your particles are in a specific position. So as you move this way, the kinetic energy is increasing and the potential energy is decreasing, because now you don't have your particles in a specific position, they are moving around. Okay? So this here can happen moving in this direction, increasing the temperature. Okay? Increasing the temperature is going to start breaking intermolecular forces between the particles of a solid. And when you break all of the intermolecular forces that you have between the particles, you will get something that it's a gas. So we have different types of intermolecular forces, and there's going to be a variation of strength, okay, between all of these different types of intermolecular forces. So I'm going over them. Like majority of the books, you will find them from the strongest one to the weakest one. I'm doing the opposite. Okay? This is the weakest out of the four that I'm going over. So dispersion or London forces are present in every substance. This type of IMF is due to the movement of electrons, and everything contains electrons. So they're going to be present in everything. So then, depending on the type of substance that you have, we're going to move from dispersion to more specific intermolecular forces. So this is the very general one. So this one here happens in everything, and I have here like an example to show you what's actually happening. Looking at helium, because we have only 2 electrons, and it's easy for me to draw like a diagram. When you have a uniform distribution of your electrons around the nucleus, right, your atom is not going to present any charge displacement. Now, if your electrons, since electrons are dynamic, which means that they're moving around all the time, it might happen that your 2 electrons are close to the same location around the nucleus, to the same location. When that happens, since you have only 2 electrons, if they're both close to one location around the nucleus, that side is going to be like more negatively charged because your electrons are negative charges. So if your 2 electrons move towards that side, then you're going to have an instant dipole. That's what's happening here. Instant dipole means that your negative charge will move to one side, and then the opposite side will become slightly positive. Okay? So it's an instant charge because your electrons are moving around all the time, which means that that here can move here, and your negative charge will be displaced towards that side and the positive to the other side. Okay? So this is your dipole. It's an instant dipole, and I'm going to show you, like, when this happens, this is like a chain reaction. If you have only one atom of helium right there, your electrons move towards one location, both of them. Your atom will become more negative on one side and positive on the opposite side. If you have a bunch of helium atoms in there, when that atom comes close to another helium atom, if your electrons are close to this side, negative charges, they repel each other. So your electrons will move to avoid the repulsions. Now, your helium atom, the second one here, will have a slightly positive side because the electrons are on the opposite side. And you can have an attraction between those opposite sides that you have in one helium atom and the next one. So this one here can come close to a third helium atom, and something similar will happen. If you have a negative side here, right, your electrons in this third helium atom are going to move far away to avoid the repulsions, giving you a slightly positive, slightly negative side. And then your opposite poles, right, they can feel an attraction. And look how I have my orange line between the negative side in the first atom, positive side on the second one, negative on the second with the positive on the third one. Opposite poles are going to attract each other. And the attraction that you have between the negative and the positive in two different atoms, that's an intermolecular force right there. And it's specific. The specific type will be your dispersion force. Okay? Now, it's an instant dipole, and it can happen like as a chain reaction, and it will happen in everything that contains electrons. Okay? Now, the relative strength of your instant dipole, it's going to depend on the size of the particle that you have. If it's an atom, you can look at the periodic table and you have an atomic size trend that you can predict using the periodic table. But usually as you increase the number of electrons, the size is going to be increasing. If you have molecules, you can actually look at the molar mass. The molar mass gives you an idea of how big something is. The bigger the molar mass, the bigger the size. That's what we usually use. So, polarizability of a molecule, it's that property of your movement of electrons around the nucleus. So the bigger your atom, the less attraction your electrons are going to feel by the positive nucleus, because you have a large distance between your positive nucleus and the electrons, okay? Which means that since you have a lower attraction between your positive nucleus and the electrons, it's something that is super big, your electrons can move around easily, right? They can move around because they almost feel no attraction for that positive nucleus that is far away from them. The opposite is also true. When you have a small atom like fluorine, your positive nucleus is super close to the electrons around the nucleus. So your electrons, they do feel a strong attraction for the positive nucleus, and they don't move around as easily as something that has a bigger size. So if you have only dispersion that's the only IMF that you have between the particles, you can actually look at the size to determine how strong your dispersion forces are. The bigger the substance is, the stronger the dispersion forces. So that's the first one, and you will see some examples where we are going to identify which types of IMFs you have depending on the substance. The second one, now this one is more specific. Dispersion you have in everything. Now you need to check your substance, and you're checking your substance to see if you have polar bonds. So polar bonds, and this is something that it's discussed in your chemical bonding. Polar bond, it's a bond where you have an actual permanent charge displacement. As long as your chemical bond exists, you're going to have two poles, one positive, one negative. Your polar bond form between atoms that have a significant difference in electronegativity. The electronegativity is the ability of an atom to pull electrons towards itself. Okay? So if you have an atom that it's very electronegative in a chemical bond, that atom with a high value of electronegativity is going to, those two electrons that it's sharing with another atom are going to be closer to that atom that is very electronegative. Okay? So your very electronegative atom has the ability of pulling electrons in that chemical bond closer to its nucleus. Okay? And you have a polar bond because now you have a charge displacement. Your electrons are going to be closer to that electronegative element in your chemical bond. Your electrons are negative charges, so that side of your chemical bond becomes very negative. Okay? And we assign a delta minus. Okay? The delta, when you have a charge displacement, the deltas, the symbols, represent that those are not ions, it's just charge displacement. Okay? not transfer of electrons. That's why we use a delta plus, delta minus, not a positive or negative. Positive and negative we use with your ions. Positive charge, negative charge, because there's transfer of electrons. If it's just charge displacement, then we use the deltas, plus and minus. So I have here a list of polar bonds, and this is not always true, okay? This is for my classes. For my classes, I do polar bonds versus polar molecules. First thing that you need to identify if you have a polar bond. If that's true, now you need to check if your actual molecule is polar. If your molecule is polar, then it means that you have your dipole-dipole intermolecular force. But for me, for our class, if you have a polar bond, I'm not going to give you a molecule with a polar bond that is not polar. That's not going to happen. If you identify one of these polar bonds, then you're going to have dipole-dipole. So this is a summary of polar bonds. You can find them using the periodic table, but you should know these ones by memory. It's the same for atoms, but combined with hydrogen and with carbon. A super important non-polar bond that you should remember, it's CH. Non-polar, difference in electronegativity between carbon and hydrogen is not, it exists, but it's not so big that will give you a polar bond. Okay? Difference in electronegativity for these 8 bonds here, it is significant. Your elements, the ones that are more electronegative or that they have a higher value of electronegativity, and you can look at the periodic table, electronegativity in your periodic table, it's increasing as you move to the right and as you move up in the periodic table. And we have a fluorine as the most electronegative element in the periodic table. So looking at the periodic table, all of these atoms here, the nitrogen, the oxygen, the fluorine, and the chlorine, all of these ones in your chemical bonds are the most electronegative ones. Since those are the most electronegative ones, they're going to have a partial negative charge. Your electrons are going to be closer to these ones in those chemical bonds right here, because these ones, they have a higher value of electronegativity. Since your electrons are closer to this side of your chemical bond, where you have the most electronegative atom, that's a negative, the partial charge is a negative, forming one side of your pole, right? Negative. And then the atoms with a lower value of electronegativity will have a partial charge that is positive. So in these 4 here, higher electronegativity for these 4, lower electronegativity for the carbon. So again, these ones will have a negative. Your pole is a negative side on those atoms, and then the positive will be on the carbon. So HCl, I'm showing you specifically this one, but that happens with all of them, with any of these bonds here. Sharing 2 electrons between hydrogen and your chlorine. Your 2 electrons in that chemical bond are closer to the chlorine because this one is more electronegative. And that's your negative pole. And since your electrons are closer to that side, this one here becomes slightly positive. So these intermolecular forces are between different particles. So I have an example here, and you don't need to have exactly the same substance. I will give you an example later where you have different things. HCl, 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 you have a polar bond, and a polar bond. Slightly negative, your pole that is a negative, it's the most electronegative one out of the 2 atoms that are sharing the electrons. And then you have your hydrogens as positive. So just looking at that one, you have your polar bond here, you have your polar bond here, you have a polar bond here. That's your polar bond. Dipole-dipole interaction, it's the interaction between polar bonds in different particles. So you have a polar bond here and a polar bond here. Negative in this particle feels attraction for the positive in this one. Positive here feels attraction for the negative here. And it's not just these ones. All opposite poles will feel attraction for each other, which means that I didn't write it down, but this negative feels an attraction for that positive. But your intermolecular force dipole-dipole is not this positive and that negative. That is a charge separation in a chemical bond giving you a polar bond. Your dipole-dipole happens between different particles. Opposite charges in different particles, they will feel an attraction for each other, giving you a dipole-dipole interaction. So my dash orange lines here represents those IMFs. And in this case, those IMFs are specifically dipole-dipole, because you have a dipole in this particle, a dipole in this one, so dipole attracts dipole. Dipole attracts dipole. Okay. The third one is a specific type of dipole, and it's called hydrogen bond. So if you have your polar bonds, you're going to check, okay, I have one of my 8 polar bonds. If that polar bond that you're identifying is any of these 3, your particle will have dipole-dipole and also hydrogen bond. Your hydrogen bonds are a stronger type of dipole-dipole. You still have dipole-dipole attraction because you have the charge displacement in your polar bond, but your dipole-dipole is a hydrogen bond. Okay? So you're going to check your molecule. Do I have a polar bond? Yes. Is that polar bond between hydrogen and nitrogen, hydrogen and oxygen, hydrogen and F? If that answer is yes, you also have hydrogen bonding. If for example, what you have, it's your polar bond, it's carbon with oxygen, that one is not listed here. So you do have dipole-dipole, but you don't have hydrogen bond. Okay? So in this one, I'm giving you an example where you have different particles. Like in the previous one, I just drew HCl with HCl with HCl. But this works also between different particles. As long as you have polar bonds, regardless of the substance that you have, if you have polar bonds in 2 different substances, you will have charge displacement and you will feel attraction between your opposite charges. So I have here, and I know it's hard to see because I already drew the intermolecular forces, but I started with an HF and a water. And in water, you have your oxygens and your hydrogens. Oxygen is the most electronegative out of your oxygen and hydrogen. So that will be your negative right there in your oxygens. And then your hydrogens will be positive for all the waters and for all of your HFs. Hydrogen is the least electronegative, so that will give you your the pole that has a positive charge, or the positive side of your dipole. And then the most electronegative atoms are the ones with my negative delta minus. So I have my oxygens and my Fs. Okay? So if you have a mixture of HF and water, since you have a polar bond between HF, that's a polar bond, between OH, that's a polar bond, so you can have intermolecular forces between your opposite charges. If you're looking just at that water molecule, those are polar bonds, not dipole-dipole or hydrogen bond, polar bonds in your water molecule. If you check the interaction between your water molecule and HF, now you have particle 1, HF, particle 2, water. Attraction between your two different particles will give you your IMF. So I have here attraction between my negative F in my HF and my positive hydrogen in my water molecule. That attraction between your opposite charges in two different particles will be an IMF. Now your IMF right here, it's between an F and an H. FH is listed right here, HF. So that attraction, it's a dipole-dipole, and it's also a hydrogen bond. So all the lines that I drew here, a negative, positive, opposite charges, are going to be dipole-dipole and also hydrogen bonds because the type of atoms that are attracting each other. H with O. HO, it's a polar bond, and it's listed as a bond that you need to have for you to have hydrogen bonding. So I have here an additional one that I didn't draw, and this works between all opposites. So positive here with the negative, it's the H and the F. HF, that's a special type of dipole, which is your hydrogen bond. So in these ones we have dispersion, because dispersion is present in everything. We have dipole-dipole and also hydrogen bonding, because out of my polar bonds I have these attractions here, and those are going to give me hydrogen bonds. So that's the third one. And then the easiest one for you to recognize after dispersion, which is present in everything, is the ion dipole forces. For you to have ion dipole forces, you need to have an ionic compound, and you need to have something else, which is a compound containing a polar bond. So you can have an ion attracted to a dipole in your polar bond. Okay? So this here is super important for solubility, which is something that we're going to look in the future. Okay? So if you have only water molecule, which is what I have here on my left side, you have your polar bonds in your water molecules, and then between your different water molecules, you're going to have your dipole-dipole and your hydrogen bond attractions, right? Your water molecules, they are held together between them by dipole-dipole, hydrogen bond, and dispersion forces. I didn't write it down, but there's also dispersion. Now, if you have your container with just the water, and now you add to that container sodium chloride, which is just table salt. Sodium chloride, it's an ionic compound. You have your ions Na plus 1 and Cl minus 1. Okay? So I'm just writing down 3 molecules for water. I'm adding 3 moles of sodium chloride, but the amount is not important. What is important is the attraction and which interactions you have between your particles, okay? The water molecules and the ions from your ionic compound. So I have my water molecules, and they are attracted to each other by your dipole-dipole and your hydrogen bonds, which is the H with the O, the H with the O, because they have opposite charges, right? Your poles are the positive side on the hydrogen, the negative on the oxygen, so there's an attraction between your opposites. Now, your oxygens in your water molecule, they are partially negative because that's the most electronegative element of your bond. Since you have that partial negative charge in your oxygen, your positive ion is going to feel an attraction for that negative atom in your chemical bond. Or the negative means that you have the negative pole on that side. And then your negative ions here, they're going to feel attraction for the atoms with a delta plus. Okay? So I didn't write it down, but all of your hydrogens are delta plus, and I'm going to write down just these three to simplify this here. And your oxygens are going to be delta minus. So your opposite ions, right? The ions with the opposite charge will feel attraction for that atom, and they should be negative. So in your polar bond charge displacement, the most electronegative atom becomes slightly negative, and then the least electronegative becomes slightly positive. Now when you add your ionic compound, your positive ion will feel an attraction for your negatives, and your negative ions will feel attraction for your positive, like HCl. That attraction between your positive ion and the negative side in your polar bond, it's an ion dipole. You have your ion attracted to your dipole here. You have your ion attracted to the dipole that you have between O and H. So ion dipole, that happens when you have an ionic compound in the presence of a compound that contains polar bonds or a polar molecule. And this is super important for your solubility. If you have something like sodium chloride, the attraction between your ions in sodium chloride with your water molecules is stronger than the attraction that you have between your positive sodium and your negative chloride ion. That's why sodium chloride is actually soluble in water. If you have something like AgCl, silver chloride is not soluble in water because the attraction between silver and chloride is stronger than the attraction that silver will have with the oxygen in your water molecule, or the chloride with the hydrogen in your water molecule. And then I have here something that you can use to simplify, like how you identify the different types of intermolecular forces in the substances. First of all, this is in general the trend increasing strength from number 1 to number 4. Okay, number 1 is the weakest one, which is your dispersion. Then dipole-dipole is stronger than dispersion. And then hydrogen bonds are stronger than dipole-dipole. And ion dipoles are the strongest out of the 4. Okay, so increasing strength as you move to the right side of my diagram here. And now I have here like a chart that you can use, and I'm going to give you some examples so you can see how I'm using this here. You should start by looking for polar bonds in the compound that I'm giving you. If you don't have polar bonds, then there's nothing else that you have to do. No polar bonds present. Hydrogen with nitrogen, oxygen, fluoride, or Cl, or carbon with the same 4. If you don't have any of those 8, that's only dispersion. Now, if you have a polar bond, you need to look further. Okay, I do have a polar bond. It means that I have dispersion and dipole-dipole. Okay, so now you have 2 of the 4. Now, your dipole-dipole. If the polar bond is one of these 3 here, it means that you have dispersion, dipole-dipole, and hydrogen bonds. If you have an ion present, now we're looking at this part here. If it's just an ionic compound by itself, that's just ionic bond, nothing else. If you have an ionic compound in the presence of something that contains polar bonds like water, then you have ion dipole. So I'm going to do CH4 right here. CH4 is bonds between carbon and hydrogen. That's it. Carbon bonded to hydrogen. Carbon-hydrogen is a non-polar bond. Non-polar. Do you have a polar bond? No, because it's carbon bonded to hydrogen, which means that for that one, you have only dispersion forces. Now, Second example, I have NH3. Now NH3 is a nitrogen bonded to hydrogen. Nitrogen bonded to hydrogen, and if you check your list, right here, nitrogen bonded to hydrogen, it's a polar bond. Since you have nitrogen bonded to hydrogen in NH3, you do have dispersion because that's present in everything. Nitrogen bonded to hydrogen, it's a polar bond. You have one, yes, it means that you have dipole-dipole. And since your NH is one of those 3 polar bonds that you have listed for hydrogen bond, out of your 8 polar bonds, if you have any of these 3, you do have hydrogen bond. So you have hydrogen, nitrogen. Hydrogen, nitrogen means that you're going to have H bond. And then in my third example here, you have carbon bonded to hydrogen, that's a non-polar, but you have oxygen bonded to hydrogen. Okay, so if you have only CH3OH in your container, OH, it's a polar bond, you have it listed. So you're going to have your polar bond in your molecule 1, and you're going to have a polar bond in another one of this one, and you're going to have many of them together. So all of those polar bonds, you have charge displacement, and you can have attraction between your polar bonds in different molecules, giving you a type of IMFs, which is dipole-dipole. And since your polar bond is OH, that's listed right here, which is going to give you also hydrogen bond. So for the last one, you do have dispersion because that one is present in everything that contains electrons. And dipole-dipole, and also hydrogen bond. So you're going to try to identify the intermolecular forces that you have in this one. So we have here identifying IMFs. This is what we did. And then I'm going to do a second video where we're going to see the effects of the intermolecular forces on different properties, like melting point for solids, boiling point for liquids, vapor pressure for liquids, and also solubility.